start the recording. A couple of reminders. So the first test is scheduled for next Thursday. So that's the 14th. So yeah, it'll just, of course, cover chapter 28. It'll pretty much just be one of each type of question. So we've basically covered 8 sections. So it'll be around 8 questions. The only exception is the trig substitution, I think, is either not on the test or it's simply a bonus question, because those ones are a bit too long, especially for like a 2-hour test. So next Thursday, I'll just send you the test in the beginning of class, and then I'll activate Dropbox, and then you just have to send it back within 2 hours. And then I'll be available over email in case anyone has any questions. So that's what we're doing next week. Today, I think we'll just do a bit more review. And then I think next week on Tuesday, if no one requests any more review, we'll probably just start on something new because I don't want to get too behind. So that's the that's the plan for now. So I guess we don't have, no more assignments at this point. And I think we already did the last participation, or the 4th participation. We took that up, so we're good to go on that end. Okay, so let's start. And if there's any questions that anyone wants to go over, please let me know. Okay, so whiteboard, sharing, good. Okay, so what I'm gonna do is I'm just gonna flip to random sections and we'll try some random questions, because on the test you do have to know which formula to use and stuff. That's not really the hardest part, because again, it's pretty much just one per type of formula. But we'll do a bunch of random questions and we'll try to figure out which formula to use. So here is the first one. Hold on, let me just get my writing thing properly set up. This is annoying. Okay. Ugh. Darn it. Okay. So this first one is, let's see, solve the integral of dx. This is annoying me. Sorry, I just have to fix this. Clear this. So annoying. Okay, I'll try my best. What is wrong with this? Trying again. Okay. Integral of, so this one's a pretty easy one. It is a definite integral. So you got a 2 up here and a 0 up there for your upper bounds, and you got dx over 8 minus 3x. So we're starting off with one of the simplest questions I could find. So the question is, first we have to figure out what formula would we use in this case. So this one, obviously, it doesn't look like a trig substitution. It doesn't look like anything that involves trig. It doesn't look like it involves the e or the exponential function. It looks like it would either be maybe a general power formula, but even that in this case, it doesn't look like it. So what I would jump to would probably be the ln formula, because the ln formula is when you have du over u. And in this case, that's pretty much what you have, because the derivative of the bottom will end up, it'll have a constant and it'll have a dx in it. So in this case, that's where my brain would jump to. It would jump to the logarithmic formula, which is, sorry, my volume keeps changing. Hopefully that's good. Okay, so it is ln of, let's see. Oh, sorry, no, not ln. It starts off with integral of u over du, or am I getting into the wrong order? So yes, very bad memory. Let's see. Oh, yeah, I did get it in the wrong order. Okay, integral of du over u equals ln of absolute value of u plus c. So that's when you know to use the ln formula when you have something on the bottom and you have the derivative of it on the top. So let's check that that's indeed what we have. So let's set u as the bottom. So u is equal to 8 minus 3x. And let's see what du is. So du equals, so of course the 8 diminishes to 0. And then the derivative of minus 3x is minus 3 dx. Which is what we have on top, with the exception of a constant, but that's something that we can always fix for. So in this case, we do need a minus 3 on top. So I'm just gonna, in order to avoid rewriting this, I'm just gonna put a minus 3 on top. and then I'm going to put a minus 1/3 outside of it. So the numbers would cancel each other out, and the minus signs would cancel each other out as well. So it's still the same as what we had. And then we can go ahead and integrate this. So this is going to be minus 1/3 ln of absolute value of u. I don't need a constant at this point. And for now, I'm just going to reinsert the original variable, and then I'll put up the two lines for the upper and lower bound. So let's do minus 1/3. Let's do one of those lines, and then ln of absolute value of 8 minus 3x, and that, and then up another big line, and then you got 2 and 0 for your upper and lower bound. So that looks good so far. When you're doing a definite integral, you don't need to include the constant, because even if you included the constant, it would, because it's first thing minus second thing, it would cancel itself out. So it would end up being irrelevant regardless. And then you just plug the 2 in and plug the 0 in and see what you get. So maybe we'll just do that to save room. Let's just do that off to the side. So for 2, within the ln, it would be 8 minus 3 times 2. So that would be 8 minus 6, so that's 2. So, okay, that's not too bad. So that's the first one. And let me know if I make any arithmetic mistakes, because that often happens. So let's put minus 1/3. Let's just leave it outside of the brackets. That's what I always do when we're in this situation, because there's no point in keeping it kind of in the brackets. So this will be ln of 2. That's what we just figured out. Minus, and then if you imagine 0 going into there, that will be ln of 8. So ln of 8, and your bracket. And then in this case, what you could do is you can combine these. So remember, there's that old ln formula, which is ln of x minus ln of y is equal to ln of x over y. So you can take, you can kind of separate the lns into subtraction, and you can kind of compress them as long as you change it to division. So in this case, again, let's just keep the minus 1/3 sitting there. And for ln, you can just do ln of 2/8. So that is the same thing as minus 1/3 times ln of 1/4, or you could say ln of 0.25. And for the answer, I guess that's a good answer. Yeah, I would accept this as an answer, because again, with ln of anything, you're basically just going to get an irrational number. If you wanted to go fully go to a numerical answer, then you just go in your calculator, type in ln, type in 0.25, it equals, and then multiply that by -1/3. So multiply bracket minus 1 divided by 3 and bracket equals, and you get, for an actual number, you get 0.462098. So either one is fine. Okay, so that was the first one. So that was just the basic logarithmic form. Looks like there's another interesting one here. Let's do this one. Okay, so let's see. Integral of, so this is another definite integral, so that's unfortunate, because those are always a little more work. So pi over 2 to 0 of cos x dx over 1 plus sine x. Okay, so first thing you should notice is, of course, the derivative of sine is cos. So you do have a thing on the bottom, and you have the derivative of it on top. So you could probably guess that this is just from the same section. It's just a question that looks a little bit different. So in this case, indeed, you can use the logarithmic formula. So just because something has a trig function in it doesn't necessarily mean you're going to be using like the fancy trig formulas or anything. Sometimes you just use the logarithmic formula or the general power formula. Just depends on what works. So in this case, let's go through this, make sure it's set up all good. So u should be, and actually here, let's write the formula again. Let's see, so that's du, integral of du over u equals ln of absolute value of u plus c. So that's our formula. So u is the bottom, whatever the bottom expression is, so 1 plus sine x. So du is, so derivative of sine is cos, so cos x dx in this case, and that is exactly what we have on the top. So good, I guess we don't really have to do much. Yeah, don't have to do any adjustments. So let's just write the answer. So this will be, and again, for now, I'm just going to leave out the bounds and I'll put them in a second. So ln of absolute value of u. So that's ln of absolute value of 1 plus sine x. And now let's put in the bounds. So this bound, pi over 2 and 0. So it looks like in this case, you could, this is just a side note, but it looks like you could ignore the absolute value sign, or you could omit it in this case, because sine only bounces around between -1 and 1. So even at sine's lowest point, what's inside of the ln would still be positive, because you'd at most get 1 plus -1, which is 0. So that's just a side note that in this case, it looks like whatever is in the ln is going to be positive regardless. So you could omit the absolute value signs, but there's not much of a point in doing that. It's just for notation's sake. Okay, so now let's, okay, so this is definitely a weird one because we got a ln inside of a trig function, or a trig function inside of a ln, rather. So let's figure this out. Let's just do this again off to the side, just to save time. So let's imagine plugging in pi over 2 into this expression. So that's 1 plus sine of pi over 2. So that is, so what is pi over 2? I'm just trying to remember. Okay, I gotta draw the graph, or you could use a calculator. But if you do use a calculator for this one, this is pi over 2. So just note that it is in radians. Make sure your calculator is in radians. Generally, when you're plugging anything into sine that doesn't have a degree symbol, then it's in radians, especially if it involves pi. Okay, so let's draw the sine graph. Just do a small one right here. See if I can remember it. 0, pi, 2 pi, and then it goes like this. And then let's see. So it looks like pi over 2 is going to be 1. Yeah, it looks like that's roughly, let's double check that on our calculator. Is this in radians? No, it is not. So I have to fix that. Shift. Darn it, how do I? Okay. I don't know how to change it on my calculator. Well, pi over 2 is same thing as 90 degrees. So I'll just use 90 degrees on my calculator. Sine of 90 degrees is 1. Okay, perfect. Plus 1. So that part is going to be 2. So that is equal to 2. So that'll just be ln of 2. Okay, so that's not bad. And then minus, and the next one ln of, so then you plug in 0 into the 1 plus sine x. Sine of 0 is just 0, as you can see at the graph, because it starts at the origin, starts at the 0, 0 point. So that's just going to be ln of 2 minus ln of 1. And if you combine those using the previous ln formula, it'll just be ln of 2 over 1, which is just the same thing as ln of 2, because ln of 1 is just going to be 0. Ln of 2. So that's a really, really nice answer, actually, ln of 2. And then again, if you wanted an actual numerical answer, type in ln of 2 and you get 0.693147. So those are 2 of the logarithmic formulas. So those weren't too bad. Let's flip to another section. Let's do something with trig. Yes, let's do this one. And I'm just making sure we're still recording. Good. Okay, let's get rid of this. And so this one is 3 cos cubed, and then for some reason they use t for the variable dt. Okay, so 3 cos 3t dt. Okay, so for this one, let's go through a couple of things. I mean, one thing that could potentially be an option would be the general power formula because you have an exponent here, but you would also need the derivative of whatever is raised to the exponent. You would need that sitting next to the expression. And in this case, you don't have that. You would need a sign somewhere in here if you wanted to use the general power formula. So this looks like one of the ones where you got to use some trig identities in order to solve this, because nothing else would really jump out in this case. It's not an inverse trig function. It's not a substitution problem because it's substitution problems start off as algebraic problems and then you substitute in trig function. So in this case, let's use some trig identities in order to solve this. And there's one that kind of jumps out because you can separate cos raised to the 3. You could separate it into cos squared times cos. And then that's a really good position to be in because we know that you can replace cos squared with 1 minus sine squared. That's one of the most common identities. And we did that a ton in the trig substitution. It was kind of an incidental part of trig substitution. So I think in this case, that's what we should do. But again, to avoid rewriting this, I'm going to, first of all, I'm just going to put the 3 outside the integral. Cos 3t dt. Let's just take the cos 3 and let's just put it off to the side and let's just try to manipulate it just so I don't have to keep rewriting the integral. So cos 3 t. Oh, and I was marking assignments yesterday, I think for this class, and I noticed a mistake that someone made that kind of jumped out at me. Someone basically wrote the equivalent of this. Someone thought that this following statement was true. They wrote cos of 3t, or sorry, cos of 3t is equal to cos of 2t plus cos t. They basically wrote out that statement. So you can't do that. That is not correct because exponents denote repeated multiplication. So you can't separate them with division with plus signs. So doing something like this in general is not correct. So just as a side note, it's just something that I remember. So let's erase this. What you can do is you could separate it as long as you separate it using multiplication. So let's do that. So this is equal to cos of 2t times cos of t. And then you're good to go. So just kind of make a note of that. It only works with multiplication. And now we can take cos raised to the 2t and replace it with 1 minus sine squared t. And that just comes from probably the most common trig identity, which is sine squared plus cos squared equals 1. Is that? Yes, exactly. Yeah. And then you can rearrange it a little bit and you get cos squared is equal to 1 minus sine squared. So that's the identity I'm about to use. And that's just listed on pretty much all the formula sheets. Okay, so let's put that in. And obviously I'm just using shorthand to save time. Okay, so cos squared will be 1 minus sine squared t. And then the other cos will just sit there. So let's evaluate this and see if this looks like a good route to go. It does look like, yes, it looks fairly good because you'll have a cos, which is easy to integrate. And then you'll have a sine squared and a cos, which also looks like it's fairly easy to integrate because that looks like it would just be the general power formula. So if you imagine the two expressions that you would get from this, it looks like they both seem reasonable. But of course, let's formally expand the brackets. So it'll be, so we can expand the cos to this and we can expand the cos to that. That's to expand to both of them. So this will be cos of t minus sine squared t cos t. Okay, and now let's do the actual integral part of this. And for the 3, should I write the 3 or should I just put it in at the end? I'll just put the 3 outside the integral and then we'll just do everything in brackets. 3 bracket, and now let's apply an integral to each of these, and I'm just going to separate the integral right away just to save on rewriting. So integral of cos t dt minus integral of sine squared t cos t d t and bracket. The only reason the brackets are there because the 3 technically applies to both of them since it was sitting in front of the whole original integral. So I'll just do the whole thing in brackets, and the 3, as per usual, can just sit there and do nothing. Okay, so 3 bracket. Now let's try to solve these. Antiderivative of cos. So derivative of sine is cos, so that's just going to be sine. Okay, so that's fair enough. So that's sine t, very good, minus. Next one is, so you have sine squared next to cos, and derivative of sine is cos. So in that case, you have it in the form of, here, I'll just write this at the top. You have it in the form of u squared du without having to even make any adjustments. So that's actually really nice. So that's just the general power formula. And in this case, it works because you have your u squared, and then you specifically have derivative of u sitting next to it. So in this case, just add 1 to the exponent and divide by that number. So this will be sine of 3t, and then divide by that number. So I'm just going to put a 1/3 right here, and then end our bracket. So this looks so far so good. Okay. And now let's expand out the original 3. So the 3 will go to the first expression. So that's just 3 sine of t. Oh, and I forgot. I need once I integrate it, I need the constant. So plus c. Technically, the constant should be there right when the integral disappears. But as long as it's in your, at the very least, if it's in your therefore statement or your final answer, then that's fine. Okay, so this is going to be, and then, so the 3 expands here, it expands here. So that's actually nice. You get some cancellation. 3 and the 1/3 will cancel. So I'll just do that automatically. So that's minus sine cubed t plus c. So I think that is correct. Let me just double check. Let's see. So 3 sine of t minus, yes, perfect. Okay, good. So that was from 28.5. So that was the section called Other Trigonometric Forms, where we had already covered kind of the basic trig integration formulas. And then this section gave you some identities that you can use when you have more complicated ones like this. So I think let's go to another one, just because these ones tend to be kind of long. Random section. Let's go to this section. Okay. Let me just pick a question here. Let's do number 6 from section unspecified. Get rid of this. Okay, so integral of cosecant 8x, so cosecant 8x, cotangent 8x dx. The 8 here seems to indicate that it's not going to be a particularly sophisticated question, just because usually when you have like an 8 in there and it looks like this, usually all you really have to adjust for is the 8 in the end. So in this case, what do we use? Let's see. First, I'm going to check to see if this is literally just listed as a formula in itself. This might just be an actual formula and we could just directly get the answer. The only adjustment we'll have to make is we just have to take the 8 into consideration. So it looks like this is, yes, this is just a pre-existing trig formula. Let me write it down. So this is on page 859. So it says the integral of cosecant u cotangent u du is equal to minus cosecant u plus c. So that's what I mean when I say it's literally just directly a formula, and that's it. The only thing, so now let's take the 8 into account, because you need a du sitting next to it, and u is 8x in this case. So du is going to be 8 dx. So it looks like we need an 8 dx in there. And that's kind of always the case when you have a number inside a trig function like that. It's like rushing nesting dolls where like the number will always pop out because of the way the derivatives work. So again, I'm just going to, in order to avoid rewriting this, I'm just going to put an 8 in here and then I'll offset it. Let me just erase the dx so I have room. 8. So let's put an 8 in there. So 8 dx. I'll put brackets around that just so it looks nice. And then let's offset it with 1/8. And then it looks like that's all we have to do. And then it's just using the formula. So this one's, okay, this one's not bad. So 1/8. And then I'm just going to put, so there's a minus sign in the formula. I'm just going to put it out in front of the -1/8, just so I don't have to use brackets. So we got the minus sign, so cosecant u, so cosecant 8x plus c. So it looks like that's all you have to do for that one. So that was from section 28, here I'll just write it, 28.4. So that was basic trigonometric forms. So that's the one where it lists like the trig formula for sine, cos. It also has secant squared, cosecant squared, secant tan, cosecant cotangent, stuff like that. So I'd recommend being familiar with these because like if I didn't know that this was a direct formula, I wouldn't really know what to do in this case because there's no exponents. So you can't really do any tricky trig identities. You can't use trig substitution. You can't use inverse trig functions. So this is one where the first thing I would do is like, let's just see if it's an actual formula. And it was. Let's go to another random section. This is fun. Okay. Ooh, this is a good one. Okay. And getting rid of this. Hopefully if people are writing these down, they have time before I erase them, but it's all in the recording. So this one is just another random one. So this is 4, integral of 4, tan squared x secant squared x dx. Okay, so what to do for this one? So this one, it looks like something that someone could easily overcomplicate. Because if you wanted to, you could try putting in some trig identities, like you could probably try replacing tan squared with 1 minus secant squared, but then you would kind of create a mess if you did it that way. So I'll just give away the spoiler. This is just the general power formula. So this is just from the first section, because remember the derivative of tan is secant squared x. So really all you have here is integral of 4, and then you have a u squared, and then you do indeed have a du sitting right next to it. So in this case, if you can remember that the derivative of tan is secant squared x, then it should jump out right away that it's just the general power formula. It's just something squared with du sitting next to it. So I guess we don't have to do much in this case. There's no adjustments that we have to make. Okay, so just the answer will be, so the 4 will sit there, and then you add 1 to your exponent and divide by that number, plus c. So that, and for some reason, I always like to do it in terms of u just because it's simpler, and then I'll kind of resubstitute in the actual function. But you're allowed, you can do it whichever way you want, as long as you get the right answer. So it looks like we got a 4 and a 3. So I'm just going to put 4 over 3. And then u to the 3 will be tan to the 3x plus c. So that looks good, because if you took the derivative, the 3 would come down, it would cancel with the other 3, the 4 would remain there, you'd have a tan squared, and then you'd have to take the derivative of the inside function. So a secant squared would pop out, and the c would disappear. So in this case, indeed, it looks like it's the right answer. Okay, so that just shows that, yeah, sometimes you could kind of, it might look like a more complicated question, but it might just be, the general power formula is like a tricky one, because sometimes it doesn't look like you can use it, but indeed, a lot of the times you can. Any other interesting power formula ones? They all look kind of similar. Ooh, this is a weird one. Let's do, yeah, let's do this one. Let's do number 15. Okay, so this is integral of, ooh, we got a square bracket. Fancy. Square bracket ln of x plus 1 and the square bracket, and that itself is squared. And then you have a dx over x plus 1. Okay, so this one is another one that might look really, really tricky. You might try to use like the ln formula, but that's not going to work because in the ln formula, ln doesn't even appear in the original integral. It only appears in the answer after you integrate it. So even that's not going to work. So this is just another general power formula, because you have a thing, which is ln of x plus 1 squared. So you have a thing squared, and the thing sitting next to it is the derivative of what's inside the square brackets. Because remember, the derivative of ln is where the inside a function will drop down, and then the derivative will sit on top. So it actually is in the form u squared du. But let's confirm that. Let's formally write this out. So for the general power formula, it is u to the n du equals u to the n plus 1 over n plus 1 plus c. So that's just the general formula. And now let's see if this is in the form u to the n du. So let's set u as whatever is inside the brackets, so ln of x plus 1. And now let's take du and see if we do have du sitting next to our expression. So x plus 1 drops down to the bottom. And then on top will be the derivative, which is just dx. Perfect. So that is exactly what we have sitting next to our integral. So this is a really kind of convenient one. So I guess we could just directly use our formula. And again, I'm just going to do it in terms of u, and then I'll put in the actual original function. So this is going to be u to the 3 over 3 plus c. And I guess that's all we have to do for that particular part. So yeah, no adjustments. The exponent is correct. Okay, so that's all good. And then the answer will just be, so u is ln of x plus 1. And square brackets. In this case, we're using square brackets because there's already round brackets. So yeah, you got to use a variety to avoid confusion. So to the 3, and then there's a 3 on the bottom. I'm just going to put a 1 over 3 right here, plus c. So that looks good. There's no other simplifications I would make. There's one that you could try, but I don't even think it would be worth the headache. This looks fine as it is. Okay, so I guess there's not really even that many sections in this chapter 28 because we've pretty much just nailed about half of them. So let's keep going. Let's do another random. Yeah, I'll try to make this more random. Okay, randomness. Let's see. Let's go to this section. And ooh, this looks interesting. Okay, so let me just find a good one. Maybe we'll do. Let's do number 10. Get rid of this. Okay, so this is integral of 3 to the 1. So we got an upper and lower bound. So it is a definite integral, which are kind of a pain, but we can live with it. So 4 dx over 49 plus 4x squared. Okay, so this one should look really familiar because the formula is really, really specific. So notice on the bottom that you have a perfect square, because 49 is 7 squared. That's what the perfect squares are, when a number is like a really nice number squared. Like the perfect squares are like 16, 25, 49, 100, stuff like that. So 49 is 7 squared, so that's good. And then 4x squared is also in the form of something squared. We can factor it a little bit. So it looks like in this case, you'd be using the inverse trig functions, because that was always the form that they use. And there's a plus sign, plus there's no square root at the bottom. So your only option is to use the tan inverse function. So let's just write down that formula. It is integral of du over a squared plus u squared. And that equals 1 over a tan inverse, or arctan if you want to call it that, u over a plus c. So it looks like we're just going to be using that. Yeah, we don't need to do any trig substitution. If there was an x on top as well, you would probably have to do trig substitution, which would be definitely longer. Okay, so let's factor the bottom first, and let's see what we get. So integral 3, 1. For now, I'm just going to keep the 4 on top because that might end up being part of what we need, or maybe not. We'll see. Okay, so 49 is 7 squared plus, and then for the 4x squared, you can put brackets around the whole expression and just do 2x and just do the whole thing squared, because the square would then attach itself to the 2, which gives you the original 4, and it would attach itself to the x, which gives you the original x squared. So you're allowed to kind of extract a square from something as long as you put brackets around it, and as long as it ends up being equivalent to what it was. So now what do we have to do? So you do need a du on top. That's what the formula says. So let's just set u. So a in this case, if you compare a squared to 7 squared, a of course is just 7. U is the 2x part. It's whatever is squared. So u is 2x. So du is going to be 2 dx. Okay, so that's not, we have a 4 on top, so we're not quite there. So there's a bunch of different ways that we could do this. We don't really need to do an actual adjustment because there's technically already a 2 present on top. We just have a 4. So what I would do is, I mean, you could just formally do an adjustment if you want, like we normally do. But in this case, since there's already a 4 here, what you could do is you could kind of just separate the 4 into 2 times 2. So let's just erase the 4 for a second. So separate the 4 into 2 times 2. And I'm just going to take one of the 2's and just keep it there. And I'm just going to take the other 2 and just move it outside the integral. So it's obviously the same as what it was, but now at least it looks like it's in the correct form. We do have a 2 dx on top, which is what we need. So sometimes you could, again, if we did the adjustment the way we normally would, it would end up being the same. But I just thought in this case, since there's already a 4 there, it's a bit of a shortcut. Is there anything else we need? I guess that's it. So let's do this. So 2 will sit there. I guess I'll put these lines for our upper and lower bound. And now let's put everything in. So 1 over 7. So 1 over a, tan inverse of u over a. So that's 2x over 7. And we don't have to worry about the constant. Okay, so this answer looks like it's going to be kind of an ugly answer because you're plugging stuff into a inverse trig function, and those are a little harder to deal with. For those, I would just say use your calculator. Sometimes you could use special triangles or the definition of inverse trig functions, but yeah. Okay, so what's the easiest way to do this? For the 1 over 7, I'm just going to take that out of the lines, and I'm just going to have it join the 2, and they can just sit out there. For the 2x over 7 within the tan inverse function, you cannot remove any of those constants because they're stuck inside of the function. Sometimes I see people like trying to take stuff that's inside a trig function and they move it outside. You can't do stuff like that. It's stuck in a function. You could do that with integrals as long as it's a constant. But yeah, the constants right here they're stuck, except for this one, because that one's just sitting outside of tan. So let's just do 2 over 7. So that takes care of that part. And then upper bound, tan inverse 2x over 7. And then it's from 3 to 1. Okay, so again, this looks like it's going to be a messy answer. Okay, so 2 over 7 can sit there. bracket. Now let's plug in our first bound. So if you imagine plugging in 3, you'll get 2 times 3 on top, so you'll get tan inverse of 6/7. So just to save some space, I'll just directly write that. Tan inverse of 6/7, and then minus, and then tan inverse. And now do the next one. Next one's just a 1, so it'll just be 2/7. 2/7. Okay, so it looks so, yeah, it just looks such an ugly answer. I'm just trying to think if there's any way of simplifying this before we just plug it into our calculator. I don't think so. You can't really combine tan inverses the way that you can like change around logarithms. So there's not a lot of freedom in this case. So what I would do is I would just do 2/7 bracket, and now let's just go on our calculator. So tan inverse of 6/7. Oh, and should this be in degrees or radians? That's a tough one. Tan inverse, I'm assuming just radians because it doesn't say degrees. So see if I could figure out how to change my calculator into, oh, I almost found it.
What makes you decide whether it be in degrees or radians?
To be honest, the only time that it's in degrees is when it specifically has a degree sign. That's like my basic rule of thumb, because degrees are not super common. So if it like literally said at the end 6/7 degrees, or if it had degrees originally in the question, then you would use degrees. Otherwise, it's basically just always radians. So that's kind of how you know. So yeah, in general, just assume we're working with radians. Okay, here I finally figured it out. Okay, 2. Okay, so now it's in radians. So tan inverse of 6/7. Tan, so shift tan, that gets me tan inverse of bracket 6 divided by 7, and bracket, hit equals. Okay, so we get some number. I don't know if there's any point in writing it down. So it's 0.708626, and then minus. And now let's do, I hate questions that are so messy like this, where you have to like actually write down numbers, and then it increases your chances of making a mistake, but you know, it is what it is. So minus, and now let's do tan inverse of 2/7. And that is 0.278299, let's round 7. Okay. So ugly. Okay, now let's just figure out the whole answer. So 0.708626 minus 0.272782997 equals. So you got your answer, you got your number in the brackets. And now again, just to save time, I'm going to do the final 2/7. So I'm going to multiply by 2 and divide by 7. And we get 0.12295. So that one was, yeah, like I said, when you have like tan inverse of 6/7, it's like I don't know how to organically figure that out, because it doesn't look like anything that you could, yeah, you can't really use any special triangles or anything like that. Plus 6/7 is not a recognizable angle. Like, yeah, 6/7 radians, no one knows what that is. So when it's something like this, just throw her in your calculator and figure it out. If it was something that I could do with a special triangle, and if it was something, I would do it that way, because usually you end up getting better answers in that regard. Like you'll end up getting like a pi in your answer, so you don't just have like a bunch of decimal numbers that you have to write down. But in this case, it doesn't look like we had any choice. So that was inverse trig functions. Maybe we'll do, since we're here, maybe we'll do one more of inverse trig. Let's try to do a sine question. And let's try to avoid more of these definite integrals. Okay, let me try to find, one. Let's do number 14, because that one looks, actually, Let me think about that one for a second. So 4y, that's a weird one. And it's too weird. Darn it. Any other ones? Ooh, this one's cool. This one looks interesting. That's a weird one as well. Let's try this one. Let's try number 17. I think I vaguely remember this from a couple of years ago. Okay, so this one totally does not look like it would work for an inverse trig function. So it's the integral of e to the x dx over square root of 1 minus e to the 2x. So when you look at that, it's like, really, that's an inverse trig function, but it does technically fall in the correct form because you do have a constant squared at the bottom minus a function squared at the bottom within your brackets. So first, let's just write out the generic formula so everyone can see how it technically is in the correct form for an inverse trig function. So this is, for sine, it is du over square root a squared minus u squared equals sine inverse of u over a plus c. So if you look at the bottom, again, it doesn't really seem like it would work, but it actually does work perfectly. The a squared corresponds with the 1. So a is just going to be 1. So let's just write that down. Yeah, because 1 times 1 is just 1. So when it comes to ones, it's really easy because, yeah, square root of 1 is 1. 1 squared of 1 is 1. It's just all ones. And then for the next part, let's take the original integral and let's rewrite it slightly, just so it's even more clear that, yes, it is in the correct form. I'm just going to take the bottom. So integral of e to the x dx square root, I'll just keep the 1 the same, but for e to the 2x, you could kind of extract the 2 out of there. And this is mostly just for presentational purposes. And again, just so it's clear that it is in the correct form. So you could actually write it as e to the x squared. So you're allowed to do stuff like that. Yeah, I'd recommend maybe looking at one of the previous sections, and everyone just make sure you're familiar with like all the little basic exponential laws, because like sometimes those are pretty imperative that you know them. So now if you compare it to the original form, it's perfect. It's just it's something squared, just like we need a u squared. In this case, it just happens to be e to the x, which is a little bit unusual, but there's no rules against it. So in this case, u is just e to the x. Good, and then as the formula tells us, we need a du on top. So that's pretty easy to figure out. I mean, e to the x is its own derivative, so du is just going to be e to the x, and then a dx will pop out just for notation's sake. And that's exactly what we have on the top. So we don't even need to do any adjustments. Perfect, we can just directly go to the formula. I'm just going to put in the generic formula first, and then I'll put in all the specifics. So sine inverse of u over a plus c. I just find it easier to do it that way, but again, it's up to you how you want to do it. So this will be sine inverse, and then I just check this part and I just put in whatever I need to. So so u is e to the x, and a is 1. So there's no point in writing that. So plus c. So I guess that was a really cool one actually, because it just totally does not look like it would work for an inverse trig function, but it does. Yeah, this is the type of question that, like, if you didn't realize that it works for an inverse function, you could spend hours on it, and I don't think you'd be able to solve it with any other methods. Which is why in university, I always had the rule that I would only work on a problem for 10 minutes before moving on. Yeah, let's see. So that was really good. I think we'll just do a few more and then we'll just call it a day. I'm a bit tired. I was up all night trying to feed my Python banana, and he has not eaten in almost 4 months. So I'm getting concerned about him. Soon he's going to be I guess not skin and bones. I guess a snake would be scales and ribs. Anyways, okay, so what have we not done? Let's go to, oh, I know what we haven't done. Okay, let's do one of these. Okay, this one's a super, super basic version of this formula that we're about to use. So we'll start off with something simple. Integral of theta cos theta d theta. So what the heck do we do with this one? Normally, I would just say just directly use the cos integration formula, but you can't because there's an extra theta sitting next to your cos. If it wasn't there, then you would the answer would just be, I guess, minus sine theta plus c, and that's it. But this theta to the left of our cos is absolutely messing everything up. And sometimes people try to just like take the theta and just move it outside the integral. And again, you can't do stuff like that. It only works with constants. And that just stems from the fact that when you take the derivative of something, the constant just sits there in front of it. That's why you're allowed to take constants out of integrals, but you can't do it with variables. So in this case, let's think for a moment, what to do. In this case, we have a function, theta, I guess it technically counts as a function, sitting next to another function. Oh, let's see what someone suggests in the chat. Someone said parts, and yes, absolutely, integration by parts is the way to go in this case. And the giveaway is when you have a function sitting next to another function, and one of them is easy to integrate, and one of them is easy to, I guess you could say, anti-derive or anti-integrate. And that's what we have in this case. This is probably one of the simpler versions of using integration by parts, because the functions here are super, super simple. It's just a variable and a cos. So let's just write out the integration by parts formula, because I can never, ever remember it. Actually, once I write out the initial form right here, then I can actually remember it. But otherwise I can't. So this is integral of u dv equals u v minus integral of v du. So this is one that I recommend you practice, because the initial setup of this is what always screws people up. So again, you have to pick something that is easy to derive, and then you have to pick something that's easy to take the antiderivative of. And you have to assign one specifically as u and take the derivative of that, and you have to assign whatever's left over as dv and go backwards and take the antiderivative of that. So it's a really, really weird way to do it. Some of it is kind of backwards, but you have to get used to it. So what should we pick? I think the obvious choice in this case is just pick u as theta, because that's super easy to take the derivative of. And in regard to cos, it's equally easy to take the derivative compared to taking the antiderivative. So that's basically a tie. So in this case, it's clear that we should pick u as theta. So let's do that. So u equals theta. And then derivative of that, du, is just d theta. So that's not bad. Next part is that you assign dv as being the rest of it. This is the number one mistake that people make, where they assign the rest of it as v, and then they, go in the wrong direction. In this case, you have to specifically assign it as dv, and then you go backwards and figure out v. So it's weird, but you got to just kind of get used to it. So dv is cos theta d theta, and the antiderivative of that is that just sine? Yeah, derivative of sine is cos. Okay, so it'll just be sine. So v will be sine theta. So that all looks good. Again, if I make any mistakes, let me know, but that looks solid. So now let's put this into our formula. So it should be uv minus integral of v du. So u is, and careful when you plug these in, because people, more than half of students at this point, plug everything in wrong. So u is theta. So let's start there. Theta. V is sine theta. So let's do that. Minus integral of v again is sine theta. And then du is just d theta. So that's actually perfect. D theta. Okay, so that's really nice. Okay, so for the theta sine theta, that just sits there. That's not even an integral. That's already solved. Don't worry about that part. Then we just have to integrate sine. So the antiderivative of sine is minus cos, right? Yeah, derivative of sine is cos. Derivative of cos is minus sine. Okay, and actually, oh, that's interesting. We already have a minus sign right here. So it's up to, we got to kind of figure out if we should, how to handle that. Because in this case, since there's already a minus sign and the derivative of cos is minus sine, we could just replace this whole part right here, including the minus sign, with cos. So it kind of takes care of that part. Or there's other ways of doing it. You could kind of do it the traditional way, do an adjustment, and then some minus signs will cancel out. But I think this is the easiest way because it's already kind of taken care of itself. So let's do that. So theta sine theta plus cos theta plus c. So yeah, derivative of cos is minus sine, and indeed that's what we had because yeah, you got the minus sign in front of the integral, so that's perfect. Okay, so that one was good. So yeah, again, that's kind of the giveaway for these is it's always a function sitting next to another function where one is easy to take the derivative and the other is easy to take the antiderivative. Let's do one more of this. Maybe this one. Okay, let's do another just kind of basic one. Sorry, stuff keeps popping up. Go away. Okay, get rid of this. What the heck? Okay. Clear drawings. And let's do, so this is 4x e to the 2x dx. So again, it looks like it's in a good form to use the integration by parts formula. Again, let's just write her down. So it is integral of u dv equals uv minus integral of v du. Okay, good. So we have to pick our u and pick our v. And then there's a 4 there, which is kind of annoying. I think I'm just going to take the 4 and do what I usually do and just move it outside the integral. And it can just sit there. You could even, I guess you could even just kind of forget about it and just do the math without it. And then just at the very end, add it in. But I wouldn't recommend that because a lot of people will forget that it was originally there. So I'm going to erase the 4. And the 4 can hang out outside the integral, just because I don't want to have to involve it in the actual integration by parts thing, because it's going to just get in the way. Okay, so what to pick as u and what to pick as du. Another thing, again, should pretty much the same as the other one. X in this case is a dead giveaway. X is really easy to take the derivative of. It's also easy to take the antiderivative, but it's going to complicate it a little more because the derivative of x is just dx, and that's perfect. But the antiderivative is x squared over 2, and it's like you don't want to deal with that when you can deal with something simpler. So let's set u as x. So du is just dx. So far, so good. And now whatever is left over, we have to set as dv. So that's e to the 2x dx. And then we have to work backwards and figure out what is the antiderivative of that. So antiderivative of e to the anything is just going to be itself. The only thing we have to take into account is just the fact that there's a 2x there. So in this case, we've done so many of these, I'm going to kind of just take it for granted. I'm just going to directly go to the answer because I don't want to have to do like a separate integral for that. So that is just going to be itself, but then you're going to have to just put a 2 on the bottom to offset the fact that there's a 2x. So it's just one of those adjustments, but I'm kind of just skipping to the end of that tiny little step. So this should be e to the 2x with a 1 over 2 out front. And if you want, you could check to make sure that works. In this case, I would check, especially since I'm kind of improvising and yeah, so if you imagine taking the derivative of 1/2 e to the 2x, it would be itself, but the 2 would come down and cancel with the 1/2, and indeed you would end up with the appropriate e to the 2x dx. So that does work. Okay, you always just have to remember with numbers, you always got to make those adjustments. Okay, so now let's plug this in. So uv minus integral of v du. Okay, u is x. V is, oh, here I should write v equals, yeah, v is 1/2 e to the 2x. So 1/2 e to the 2x minus integral. So v again is just 1/2 e to the 2x. And then du is dx, perfect. Okay, what to do for the left part? Again, I'm gonna rearrange it a little bit. I just like having the number on the left part. So let's do 1/2 x e to the 2x. That just looks nice. Minus, and then for the next part, again, it's just going to be kind of similar to what we previously did, where the antiderivative is just itself, except you gotta put an extra 2 on the bottom to offset the 2x. So there's already a 2 on the bottom, so now you're gonna get a 4 on the bottom. So this should be 1/4 e to the 2x plus c. Yeah, that looks good. Yeah, that looks right. And then you could simplify your answer a little bit. You could factor out the, oh, let's see. What about the 4? Oh, you're totally right. I literally forgot about the 4. Thank you. Thank you for reminding me. Yes, exactly. Very good. There was a 4 here originally. And it's funny because I even warned that if you leave the 4 out, you might forget about it. And then I literally forgot about it. So let's just put brackets around. So this, but it's an easy fix. Let me just erase this equal sign so I have some room. So you would just put brackets around this and just put a 4 right there. You don't have to attach it to the c, because 4 times an arbitrary constant is just an arbitrary constant. So there's no point in even bringing the 4 close to the c, because it doesn't matter. And then at this point, I would expand the 4 to both terms, because you could do some nice cancellation. So if you expand the 4 to this, 4 times 1/2 is just going to be 2. So 2x e to the 2x minus, and then 4 times 1/4 just kind of cancels itself. So that's good. So minus just e to the 2x. So thank you for reminding me. Plus c. So that looks good. Oh, sorry, it should be e to the 2x. Yeah. Because there's no way to really change that in this scenario. And yeah, that looks good as an answer. So good. Okay, so let me just check to see if there's any sections that we haven't covered here. I'll just go in order of them. So number 1, general power formula, we did that. The basic logarithmic form, we did that. Did we do the basic exponential form? Let's do one of those. Which one shall we do? Let's just do a basic one. Yeah, and I think that's the only section left, because we did basic trig, we did more advanced trig, we skipped substitution, because again, that's gonna take like an hour. We did integration by parts. Okay, so we'll just do, just one last one, and then we're good to go, because it's already been over an hour. Okay, so delete this. Let's do this one. So this is integral of 2e to the minus 4x dx. So let's just write out the formula. It's probably the easiest one to remember, because again, it's just basically that it's its own derivative or it's its own antiderivative. But then of course you have to take into consideration that you need the du in your expression. So it's not quite that simple, but it's still pretty convenient. So integral of e to the u du equals e to the u plus c. So with this scenario, most of your energy just goes into making sure that you got the du sitting there appropriately. And that usually involves making an adjustment. And then the rest of it is just using the formula directly. Okay, so for this one, maybe we should just take the 2 out before we even do anything. Let's just take the 2 out and take it outside the integral. So I'm just going to erase it and put it right here. 2. Okay. Now let's just set u as minus 4x, and let's see what adjustments we have to do. So u is minus 4x, and du will be minus 4 dx. So we need a minus 4 in our expression next to our dx. So I think the simplest way is just insert a minus 4 and then offset it with a 1 over minus 4 outside the integral. And then the 2, you can simplify it with the 2, as in the next step. So in this case, let's do that. So 2 integral e to the minus 4x. Okay, so now I'm going to insert a minus 4 right here. And I'll just put it along with the dx and put brackets around it just so it's nice in terms of formatting. And then we got to offset it by putting a 4 on the bottom here. And I'll put a minus sign out front. So minus sign would cancel, 4 would cancel with itself. Good, everything is the same as what it was. Now we can just directly use the formula. So this should be minus 2 over 4 times e to the u plus c. So that's minus 2 over 4 times e to the minus 4x. Again, you could just directly go to this step. You don't have to use u, but I just like using the actual original formula first. Plus c. And then last tiny step is, of course, minus 2 over 4 can reduce a little bit. It's just minus 1 over 2. Or you could put minus 0.5. It doesn't really matter. So minus 1 over 2 e to the minus 4x plus c. Okay, good. And actually, before we're done, there's one more thing that I wanted to do because I think it's something on the test, and it's something that we've only done one example of it. So I just wanted to give a reminder to everyone, not to give away too much, but so what section is this for? We need the inverse trig section. And we need one of the ones that requires a completing of the square. Let's try to find an easy one. Not that one, not that one, not any of those, not any of those. Where are they? Not any of those. Okay, so there's one. Maybe this one will work. Oh, this one looks good. Okay, let's do number 20. Okay, so clear drawings. And then this will be the last question for our review. So integral of, so this is an inverse trig one. So 2 dx over x squared plus 8x plus 17. Okay, so it doesn't initially look like this is going to work for an inverse trig function, because usually it's a number squared plus a function squared, which we don't have at the bottom here. We have a function squared plus 8x plus 17. So it doesn't look like it. But what you can do is you could do something called completing the square, which is something that we saw that we did do in previous examples. Aside from that, I think I should take the 2 out and just leave it outside. And yeah, so for now, I'm going to erase the 2. And I'll just put it out here. 2. Okay. And let's write down the hypothetical function that we would be using. There's no square root here at the bottom. So this will be a tan inverse. So let's just write that down. Integral of du over a squared plus u squared equals 1 over a tan inverse of u over a plus c. So again, it doesn't quite look like it's going to work, but let's take the bottom expression and let's do some algebraic manipulation. And I think we can get it to look like it's in the correct form. So let's take that. Let's take x squared plus 8x plus 17. Okay, so what to do in this case? I think what we should do is take the 17 and write it as 16 plus 1, because 16 is a perfect square. 1 is a perfect square, and it's pretty convenient. And yeah, let's do that. And there's a secondary reason as to why I'm doing that, but I'll explain that in a second. So x squared plus 8x plus 16 plus 1. So it might seem weird that I'm factoring it like that, but now what we can do is we can take this part right here and do what is called completing the square. And you know that you can do this factorization process called completing the square when you have a number that multiplies to this that adds to this. So you'll notice that 4 times 4 is 16 and 4 plus 4 is 8. And that's like the little secret giveaway to let you know when you can use this completing the square factorization. So it always has to be in that exact form, where the last number is something squared and the middle number is those two numbers added up to each other. Hopefully that makes sense. So in this case, what you could literally just do is just do x plus 4 squared. And and then you'll have the plus 1 as well. And that actually, it's technically the same expression. Again, in this case, I noticed that this is 4 times 4, this is 4 plus 4, and that lets you know that you can complete the square and you'll just have a 4 in the brackets. So I remember that's like a trick I learned from high school. And now it actually is in the correct form. Or actually here, let's just write the 1 out front. 1 plus x plus 4 squared. So if you compare this to the bottom of the generic formula, we do have a number squared plus a function squared. And again, I just wanted to mention this because I can't make any promises, but I think something similar like this is on the test, and I just wanted to make sure everyone remembers completing the square. So let's complete this. So 2 integral dx. On the bottom, we get 1 plus x plus 4 squared. Okay, good. And now let's assign everything appropriately. So if we compare this to the generic form at the top right, a squared is 1. So again, a is just going to be 1. A equals 1. U squared corresponds with x plus 4 squared. So u is just going to be x plus 4. U equals x plus 4. And now let's do du. So du equals, so that's just going to be dx. Okay, so you don't need to make any adjustments or anything like that. But we do have to remember that the 2 is gonna sit there, because I forgot about that last time. So I guess we could just directly go to the formula. So 2 bracket, and as per usual, I'm just going to put in the generic version first, and then I'll plug in the specifics. So this should be, so 2 times, okay, so 1 over a, that's just 1 over 1. Easy, so that's just, we don't have to write that. Tan u over a, so that's going to be tan, and then again, a is just 1, so just forget about the a in this case. So that's going to be tan inverse of x plus 4. And oops, my brackets are getting a bit sloppy. I should use square brackets for this part. So 2 square brackets plus c. And in this case, there's actually no point in even having the square brackets. So my final answer, I'll just write it on the top left, would just be 2 tan inverse of x plus 4 plus c. So that one's a cool question. So again, I just wanted to make sure we got everything covered for the test. Okay, so that is, yeah, I think that's basically everything. Like I said, what are they called? The trig substitution will either be a bonus question or it won't be on there. I just can't quite remember at this point. Okay, so it's already 10:47, so that's okay. I think we're good to go. Okay, so does anyone have any questions? And for the test for next week, the North Bay students can also just write it at home like everyone else, and I'll be available over email in case anyone has any questions. If anyone specifically wants to write it in person, just let me know and we can do that as well. But yeah, if you're going to do that, then bring your computer, because obviously it's open book and open computer, and I want it to be equal among everyone. But for now, we'll just have everyone write it at home unless anyone wants to do otherwise. And no assignments. Okay, so I guess that's it. And then we got a long weekend. Monday's a holiday, so that's pretty cool. So everyone, I guess, thanks for coming and have a great long weekend. Bye-bye.